Wesley McGhee here. Wesley came to me last fall, was interested in doing some work in non-thesis master's research project, and we started talking about a few things, and we got interested in grass shrimp. We got interested in this saltwater grass shrimp and doing some toxicity work, and I had been doing some work with acrylamide with frogs, and I said, you know, I really don't know what this is doing with the grass shrimp or whether this system would really work the same. So he said that sounded really good to him. So he's going to tell you what he's been working on with that over the last 3 to 4 months, something like that.
Good morning. My presentation is a preliminary analysis, the toxic effect of acrylamide on the grass shrimp. The P. pujo, which is the grass shrimp, transparent grass shrimp, slightly yellowish in tint. They live mostly on coastal waters. Dr. Raven was gracious enough to lend me plenty of his. They were great for this experiment because 200 to 300 fertilized eggs per clutch, and so that once they were gravid, they gave us plenty of eggs to use for our various tests. And the hatch time is relatively quick. You're going to see later, as I'm going to talk about later, we have a 4-day hatch test and a 12-day hatch test. And so we're going to see the difference in those and maybe the toxicity that acrylamide has on the various tests. Acrylamide is a carcinogen. It is actually grouped as a 2A carcinogen. And it's mostly found, how it relates to us, is mostly found in like French fries, potato chips, cereal, and something that most everyone drinks actually is in coffee also, albeit small doses. When actually found in animals at high doses, it is causing tumors in the testes, adrenal gland, lungs, and such. So that's how that could affect actually the humans and how they inhibit acrylamide. And so my hypothesis was would grass shrimp be more sensitive to acrylamide than the zebrafish due to the relatively smaller size, meaning could they possibly metabolize acrylamide faster. And so we have to determine the LC50 for grass shrimp, determine how it compares with the zebrafish, and find a viable range for acrylamide toxicity in the grass shrimp. And our materials and methods, shrimp collection. We collected, of course, we didn't actually collect them. They were collected, of course, the Gulf Coast of Alabama. We kept them here in the fish tank in seawater, and man-made seawater. Feeding usually took place once a day. Just you can feed them regular food that you can actually find at any pet store. We collected the embryos using the microscope and just manually separate them. So that's the most tedious part of the experiment is physically separating those embryos from the rest of the clutch. We had 2 various tests. We had the first test was a 4-day hatch test, and then we did 2 12-day developmental tests. The big difference that we could possibly look at also is when acrylamide is actually placed in there in the wells with the embryos, because the embryos has a coating on it. And the 12-day test, acrylamide could lose some of the toxicity in that 12-day. The 4-day may actually be a better rangefinder. Actually, we will, and I'll talk about that later. We recorded the data daily to compare each experiment individually. Experimental design was we had 528 total grass shrimp out of all the experiments. So we had very good analysis on how they would react. We had 24 well plates, 1 embryo per well. Again, we used seawater, and we used the control, so 0.08 milligram per liter, and we placed it in a 27-degree Fahrenheit incubator. And again, it was checked on and counted every day. The analysis. This actually going to kind of go, because we had 2 12-day tests, I actually put them together. And as you can see, the control actually even had a little bit of death, not much, but once we start getting up to 0.14 and and 0.16. We usually have 100% death or close to it. Certain death is usually the 0.2. That one is that toxicity we knew would pretty much cause certain death in the embryos. The day four test. And this was actually the first one we done to give a good range find, so you're gonna have more, you're gonna see more 100% certain fatality in the grass shrimp. Again, it started around 0.14 all the way up to 0.4, which if you noticed in the previous slide that we did not go up to 0.4, we only went to 0.2. And here's just the graph, and it pretty much goes in line with the data that I spoke about earlier. The 0.2 use is normally the death threshold, right? The 100% death threshold is the 0.2. And this one is a little bit different. And it still gives you about 0.2, but actually we had 1 or 2 to survive of the 24 well plates. So that's why the graph isn't all the way at 100% for the 0.2. And this is experiment 3. It pretty much goes in line with, more in line with experiment 1. Of course, 0.15, which is right in between that 0.14 and 0.16. Again, it shows 100% mortality. And this is just the LC50, which we got about 0.15 for the 4-day test, 0.12, and 0.12 for the other 12-day test. So they're relatively in the same ballpark for the LC50. The conclusion of 3 experiments of acrylamide toxicity, 0.2 yielded 100% mortality with the exception of experiment 2. The death toll of the embryo didn't occur to hatch. Again, the acrylamide, unless it was punctured while we were physically separating the embryos, the acrylamide didn't usually cause death until actually the hatch, because it was actually able to actually physically get to the embryo instead of just being on the outside, actually able to get to the embryo. High concentrations of acrylamide cause abnormal embryos, which resulted in no hatch. Extremely high doses like the 0.4, because that dose was so high, we had more of them to not hatch or actually die during hatch, as opposed to being hatched and maybe living a day or two and then deceased. Both zebrafish and the grass shrimp yielded similar results. The zebrafish actually yielded a LCP of 0.035. The acrylamide seems to affect the shrimp more at hatch compared to the zebrafish. Once the zebrafish, they had more of their effect before they actually hatch. The shrimp actually, on the other hand, once they hatch, their effect was more felt. Most zebrafish are affected even before hatch compared to the grass shrimp. Again, those that didn't seem to die was noticeably active. So if we had some that didn't die with the 0.14, the reason that they didn't die, because of course it wasn't enough acrylamide toxicity, was they would have died past the experiment date. But those did seem noticeably less active. It took actually a lot more looking through the microscope and maybe just seeing slight twinges because the acrylamide did have that toxicity effect. Future studies. This is one of the first studies of acrylamide on the grass shrimp. And so the next step would be to see how it compares with other marine species, whether invertebrates, crustaceans, and see what maybe, are they comparable, what kind of mechanisms are related or are relatable with the various species. Next would be the testing various substances to see which inhibits acrylamide. L-cysteine has been known to inhibit acrylamide. That'll probably be our next step with testing this, or it may be another various substance that we may decide to use to inhibit the effects of acrylamide. Have any questions?